The physics behind blood pressure. Blood pressure is defined as the force that blood exerts on the walls of the arteries and veins. A healthy blood pressure is considered 120/80 millimeters of mercury. The top number is the systolic number. The systolic number represents the pressure when the heart is beating. The bottom number is the diastolic number. This number represents the pressure when the heart rests between beats. Blood pressure is measured using a cuff. This works by when the cuff is completely inflated, it does not allow for blood to flow through the circulatory system. However, once the pressure is reduced in the cuff, you reach the systolic pressure, which is indicated by a vibration in the arterial wall. This gives you the top number of your blood pressure. When it's reduced even more, you reach the diastolic pressure, in which blood flows normally, causing no vibrations. This gives you the bottom number of your blood pressure, giving you your stereotypical 120/80. As talked about before, we talked about generally what blood pressure is. However, there's a condition called high blood pressure, in which the force blood exerts on the arterial wall is too high. High blood pressure on the wall of the vessels and arteries for an extended period of time leads to damage of the vascular system by narrowing the vessels. The narrowing of the vessels causes increase in the pressure. According to the CDC, every 1 in 3 American adults has high blood pressure. Causes of high blood pressure include things such as smoking, lack of physical activity, being overweight, a high salt diet, alcohol, and simple genetics. As you see here, once the damage has occurred, plaque sticks to the scarred tissue, narrowing and hardening the arterial walls. Fat and calcium build up on the walls, which causes an increase in blood flow, forcing the pressure in the arteries to rise. Over an extended period of time, this can lead to things such as a heart attack, which are a complete blockage of a vessel or an artery. Daniel Bernoulli is a Swiss mathematician from the 1700s who created a principle that related the pressure within a system to the velocity of the fluid. So Bernoulli's principle is defined that states that the speed of a moving fluid, liquid or gas, increases, the pressure within the fluid decreases. This can be shown through the equation of the total fluid energy. So your total fluid energy is equal to your pressure energy plus your movement energy and plus your potential energy of that fluid. As you see here, the formula we talked about before, the total fluid energy, can be represented by this. P1 is your total pressure. And then your total kinetic energy is represented by 1/2. The small p here represents the density of whatever your fluid is. V, which is the velocity of that fluid, squared. And then the third aspect of this equation is the potential energy. So P once again represents that density. G is the gravitational force that is exerted on your fluid. And H is the height difference between your first fluid and your second fluid, so wherever your fluid's traveling to. As you see in this image above, you can equal two of the total fluid energies of two different locations together, and they will equal each other. So as I said before, P1 is your pressure energy, the second aspect of the equation is your kinetic energy, and the third aspect of the equation here is your potential energy. As you see here in the image below, P1 here is, we could consider is the normal wide vessel of an artery. P2 here can be represented by the narrowing of the artery due to plaque buildup. So as you see here, once the fluid is forced into a smaller area, the velocity has to increase, decreasing the internal pressure to force the fluid through to the other side. However, we can make a few changes to this equation. So due to the blood not traveling from different heights, due to it traveling within the same artery, and it'll be roughly around the same height, we can delete the third aspect of this equation out with the potential energy due to there not being that height change, which makes the equation a little easier to work with. So just a little recap of what Bernoulli's principle is. So as the speed of the moving fluid increases, the pressure of the fluid decreases, and that's represented by this formula below. So the total pressure plus the kinetic energy of that fluid is equal to the total pressure on the other side and the kinetic energy of the other side. And those two things should be equal to each other. So the differences here will be the pressure and the velocity, which will equal each other out. Okay, so let's try an example using that formula. So determine the velocity of blood flow at point B, here indicated where the plaque buildup is, if the pressure is 90 millimeters per mercury. At point A, the blood pressure is 120 millimeters per mercury with velocity of 12 millimeters per second. The density of the blood overall is 100 grams per millimeters cubed. So here, use the formula to determine what the velocity at point B will be. So using our problem solving, let's go ahead and set this up. So there's a few things we know from the example. So we know the density of the blood is 100 grams per millimeter cubed. We know the pressure at point A is 120 millimeters of mercury, and the velocity at point A is 12 millimeters per second. The pressure at point B is 90 millimeters per mercury, and we're looking for the velocity at point B. So if Bernoulli's principle stands true, then the velocity at point B should be much faster due to the pressure drop. So as you see above, we're going to need our Bernoulli's principle formula. So the pressure plus 1/2 of the density times the velocity squared equals to the pressure at point 2, which here would indicate B, plus 1/2 of the pressure times the velocity at point B squared. So as you see here, we can plug in. So we know at point A that the pressure is 120 millimeters of mercury, plus 1/2, and then the density, which is actually the same on both sides. So as you see here, we were able to cross that piece out. And the velocity at point 1 being 12 millimeters per second squared. At point B, we know that it's 90 millimeters per mercury for the pressure, and we're looking for that velocity. So we have 1/2 plus velocity, 1/2 times velocity squared here at this point. Once we do some general algebra here, we see that we reach to 192 millimeters per mercury divided by the millimeters squared per second squared. And on the other side, we have the 90 millimeters per mercury plus the 1/2 of the velocity 2 squared, which is what we're looking for. So as you see here with the final math, we reached that the velocity at point 2 is 14.3 millimeters per second, which is much faster than the 12 millimeters per second at point A. So as we determined in the previous slide in the example, we found that the velocity at point A is 14.3 millimeters per second with a pressure of 90 millimeters per mercury. This is persistent with Bernoulli's principle, in which as the pressure decreases, the velocity of the fluid increases. This can be shown as from point A, the pressure is 120 millimeters per mercury with a velocity of 12 millimeters per second, in which as it passes through the part of the artery with plaque, the pressure decreases to 90 millimeters per mercury with a velocity of 14.3 millimeters per second. So the overall physics behind blood pressure. So Bernoulli's principle relates the pressure and flow rate of blood through the arteries of the vascular system. And as we know, as the pressure decreases in the arteries, the rate of the flow increases.